This proof assumes some familiarity with vectors. It's not the easiest proof to remember, it's not the most intuitive, and if you're struggling to remember it, think symmetry. That's the thing that really makes it work. So the idea behind the proof is that we have some particle moving on a circular path with a constant velocity, and we're aiming to prove that the particle is actually accelerating towards the centre of the circle. The bold arrows on the diagram represent the particle's velocity at two separate instants, and as you'd expect, the arrows are of the same length because the particle is moving with constant velocity. Now each arrow is the particle's velocity vector at a given instant in time, and so the image captures two separate instants in time, and in that sense it's more like a video than an image, but it's just as a guide to what we're going to do, which is as follows. We're going to consider the change in the velocity vector, which we can call delta v, over some small time period, delta t. And during that time period, delta t, the particle is going to rotate through an angle 2 theta. And notice that the vector on the right there is defined in terms of components, v cosine theta and v sine theta. And those components are with respect to some x and y axes, oriented as you'd expect them to be. Now, I've written those components for the vector on the right, which is the later one in time, and it's very important to note that they would be different for the vector on the left, which is the earlier one in time. And that's just because the particle is changing direction. That having been said, however, the component in the x direction, which is v cosine theta at the later time, will actually be the same also at the earlier time. And that can be seen from the image by considering the length of the bottom edge of each of the triangles. And that length represents the magnitude of the velocity in the x direction. And since the particle is travelling from left to right in the image, it's travelling in the positive x direction, and so that component v cosine theta will be the same in both cases. And that's very convenient. That's one of the nice things about this proof. The symmetry allows that to happen. It means that the change in the velocity vector will be a change in its y component only. And again, the symmetry makes a nice arrangement for that comparison too, because consider now the vertical edges of the triangles. They're the same length, and that corresponds to the magnitude of the velocity in the y direction being the same at each instant, and therefore it only remains to consider whether the particle is travelling in the positive or negative y direction. And there we do have a change in velocity. And that change in velocity then, which we can call delta v, the difference between the two velocities, is v sine theta minus v sine theta, which is 2v sine theta. Notice that because of the symmetry of this setup, that change in velocity must be towards the centre of the circle, and so we can conclude that whatever the magnitude of this acceleration turns out to be, its direction is towards the centre of the circle. The other observation to make here concerns the distance travelled by the particle in the time delta t, and that's going to be given by the length of the relevant arc on the circle, which is r times 2 theta, where r is the radius of the circle. So now we're essentially using the distance equals speed times time formula, and there's no need to worry about angular velocities or anything here. We have an ordinary length and a linear velocity, and even if it were otherwise, as the time period delta t approaches 0, which it will do in the final calculation, the angle subtending the particle's path, which is 2 theta, also approaches 0. And under these conditions, the arc, the length of which is the particle's path, is increasingly well approximated by a straight line. Anyway, what we need from these two equations now is the change in velocity with respect to the change in time. And since we have both a delta v and a delta t term, that gets us off to a good start, and all we need to do now is squeeze out the result. In other words, after deriving an equation for delta v by delta t, we consider what happens as delta t approaches 0. Firstly, delta v by delta t approaches dv by dt. Now this is just a result from calculus about a derivative, and if you're using this proof for anything below undergraduate level, you can get away with just saying that delta v over delta t approaches the acceleration vector that we're looking for. Also, theta approaches 0, which means that sine theta is increasingly well approximated by theta. Finally, employing these two results in the equation at the top of the page, we find that the acceleration vector that we're looking for is given by v squared over r, and as we saw, its direction is towards the centre of the circle.